Now we know that M also has an activation. So we have to feed this value through the Silu activation. Now, if we go to the documentation, the Silu function consists of these two operations. X, which is the input tensor, which we just calculated, and then the sigmoid function of that tensor. So we could call the Silu directly, or we could calculate the sigmoid and then multiply by the tensor. So let's actually do this first. So you can think of the sigmoid activation function as a function that scales values using the logistic function, where the inputs are on the x-axis and the outputs on the y-axis. So if the input x is, for example, very negative, the output would be close to 0. However, if your input to the sigmoid activation function is pretty large and positive, the result will be close to 1. Now, if your input lies somewhere in between, close to 0, the output would be close to 0.5. And then, of course, values in between will correspond to values in between of this logistic function. So we can do this a couple of ways. We could run this function from scratch by just creating a function where we're actually writing literally the formula that you can see here. So if we had a tensor of value 0, then we would expect that the output of the sigmoid function would be a tensor of value identical to 0.5, as you can see here. And similarly, if we had a tensor value of a large negative number, then we would expect our value out of the sigmoid to be close to 0, as you can see here, and close to 1 if it was positive. Now, if instead of this tensor, we feed the output conv out that we just obtained, this 0.58 right here, 0.58, maybe somewhere right here, we'd expect to obtain a number above 0.5 but lower than 1. So let's run that. And we obtain 0.64, corresponding to somewhere along this curve. Now, if instead of doing it from scratch, we wanted to use the sigmoid function from PyTorch, then we could just comment this out and run that one with torch.nn.Sigmoid, defining that module, and then inputting the same conv out that we obtained above. And the result should be the same that we see here. So when we run this, we should obtain also 0.64, etc. And we do. So you can see that both functions are equivalent. Now we perform the sigmoid function, but again, here we actually need the Silu activation function. So we know that the Silu function takes the sigmoid as input. So we could just feed the sigmoid out from here and our conv out that we calculated above, and we should obtain this value, 0.374. But we could also do that using the nn.Silu function within PyTorch, where you're only feeding in the x, the input, in our case, conv out, and then the Silu activation function will perform inside the sigmoid, as well as multiply by the value that was inputted. So let's comment this out and comment this one. So we create this variable, Silu, and then we feed not the sigmoid out, but the actual input, conv out. And the result performing this should be identical to the previous method. So let's run this and see if we obtain 0.374. And we do. So you can see that they're both equivalent and you can use them interchangeably. And the Silu function takes an input that can range between negative to positive. And then the output would be this function that you see here. If the input is slightly negative, the output will also be slightly negative. And then if the input is 0, you'll obtain 0. But then as your input increases, meaning you have tensors that are firing together and are actually finding interesting characteristics within the image and within the tensors, then you want to augment, you want to activate those values even more so that you can cascade them downstream to the next layers in our neural net. So in this case, this is a linear activation. So if the input is 1, you'll get 1, 2, you'll get 2, and so forth. So you're activating the positive values and basically not giving much importance to the negative ones. So just to finalize this section, again, if we print M and then we feed our input image, the image that we loaded right here, which again is the input image that was fed here to our first stage of the neural net. Then we'll obtain the output of that operation. So let's run that. And you can actually see that if I print x.out, you can see that we get 2.86. And similarly, you can see here that we also get 2.86 and negative 5.5 and 2.86 and negative 5.5. So we know that's the correct output. But if we want to cross-reference the results, given that our output shape has been shrinked by half, we also need to get the corresponding tensor for the image patch that we provided. And if you remember, the coordinates of the image patch that we provided was 264 and 354. and 354. These were the coordinates of the patch that we provided. So given that the image got shrunk by 2, if we get the new coordinates, the coordinates of the output tensor, those coordinates will be 132 and 177. If we place it in the right index, the height and the width, and then extract that value out of our xout tensor, then we obtain the same result, 0.374, that we obtain with our quote-unquote manual method, where we perform the operations one at a time for a particular image patch and a particular kernel, kernel 7 in particular, and we're able to validate that we obtain the same result as with the direct approach.